Hello, I'm Matt Helmers with Iowa State University. Today, we're going to talk a little bit about infield practices and the impacts that infield practices have on nitrate loss from our drainage systems. This is going to be focused a bit at some of the data that we've collected in Iowa, but for which I believe is very relevant as we think about the U.S. Corn Belt and areas that we have artificial subsurface drainage, and we're concerned about the water quality that's leaving those areas, specifically nitrate, nitrogen. I am located here at Iowa State University, and I'm the director of the Iowa Nutrient Research Center and in the Department of Ag and Biosystems Engineering. So as we think about nitrate loss from our agricultural systems, I think it is important, and we think about infield practices. I think it's important for us to think about and understand how nitrate is lost from the systems and how we do need to be concerned about areas that have subsurface drainage and areas that don't have subsurface drainage. Many times in Iowa, we hear that subsurface drainage causes nitrate loss, but I would change that slightly and say subsurface drainage delivers nitrate that's lost from the plant root zone to downstream water bodies. So this illustration here is looking at, on the left there is an illustration maybe of a more naturally well-drained system where we don't have artificial subsurface drainage. And then on the right is a system that have soils with poor natural drainage. And we've put in that subsurface drainage to help us with reducing that water table, reducing excess water stress on the crop, as you've heard about in other modules of this program. So the system on the left, really the only difference between the two is that on the right, we have that artificial subsurface drain. But on the right, we have precipitation. Some of that water is going to infiltrate, and that infiltrating water is going to take nitrate with it out of the plant root zone, and then it may be lost through lateral flow to a surface water body or to deep percolation. The system on the right, we still have that infiltrating water, but it's intercepted by the artificial subsurface drain and delivered to the stream. But in both of those cases, we lose nitrate below the plant root zone. So while we may talk about quantifying nitrate loss in subsurface drainage in the subsequent slides, really what we're talking about as we think about infield practices is, does that concentration of nitrate, is it reduced as it leaves the plant root zone and then subsequently lost downstream? And so we're going to think about, can these conservation practices that we implement help us reduce that nitrate concentration leaving the plant root zone? And so as we think about practices, we kind of have to think about them a little bit differently, because in areas with tile drainage, we still need the infield end management that we're going to talk about today, and some thinking about some of our land use practices to have more green cover on the land. But we also have the opportunity of edge of field practices, which you're going to be able to hear about in other modules, where we intercept that tile drainage and treat that water before it's delivered downstream. So in some ways, in our areas of tile drainage, we have a whole nother section of practices available to us that we don't really have available to us for nitrate reduction in areas without tile drainage, because in those areas, what we're really worried about is how can we reduce just that concentration of nitrate leaving the plant root zone, and we'd have to be using infield end management or land use practices that we'll talk about here coming up. So as we think about, again, kind of these practice categories that we might have, and we're really going to focus the next half hour or so on talking about these first two broad categories, which is nutrient management. And as we think about that, we're thinking about what has been termed the 4 R's of nutrient management: the right source, the right rate, the right time, and the right place of where we're using that nutrient. And what I'll talk about is the nitrogen side. Then in some of these areas, we may be looking at land use, which may be cover crops, could be pasture and hay ground, extended rotations, maybe diverse perennials out there. Land retirement might be a conservation reserve practice where maybe we're putting prairie in. And then those edge of field practices, which again, we won't talk about in this module, but will be talked about in others, the whole host of practices of intercepting that tile drainage in many of our areas. So as we think about nitrate loss and the impact of infield conservation management, I think that this slide illustrates why we have the challenges that we do within the Corn Belt or any areas where we have annual crop production. And so this is a slide that a colleague of ours put together, Dr. Mike Castellano, that's an environmental soil scientist here at Iowa State University in the Department of Agronomy. And the red line is trying to illustrate the rate of soil nitrate production from native soil organic matter. So as soils are moist and warm up in the spring, we convert a portion of the stable organic nitrogen pool in our soils into the nitrate form. So that red line is trying to illustrate kind of the rate of soil nitrate production within our soils, these very productive soils throughout much of the upper Midwest. The green line is to illustrate the rate of nitrate uptake by our corn or soybean crop. So as our crop starts to grow, it's taking up water, it's taking up nutrients from the system, and storing that in above ground or below ground biomass. Now, if we look at that red line and the green line, if any of you took calculus, you could integrate under that curve, and the area under the curve is about the same. But most of us, that's not really what we're looking at. But if we look at that, while the area under the curve may be similar, the problem is that they're not happening at the same time. So we have this nitrate production from organic nitrogen in our system happening in the early months of the year, or early spring months of the year, April, May, but we don't have much uptake of nitrate till a little bit later in the growing season. Now, that difference in timing between when these two kind of peak might not be a huge problem, except that we get rainfall during a lot of these periods when that green line, or the red line, is above the green line. So then we have that risk of nitrate loss from our system. Okay, if we get excess rainfall during those periods, we move water through the plant root zone, we are susceptible to nitrate loss in that system. So as we think about some of the practices that we might implement, how could we reduce that gray area so that there's less risk of nitrate loss? Or how could we get the red line and the green line to match up a little bit closer together? That's kind of maybe underlying principle as we think about some of our nitrate management practices or land use practices. Okay, so we're going to talk about some results, and I'm just going to illustrate kind of a way that many people throughout the upper Midwest monitor drainage systems on replicated plots where we dig big sumps in the ground. We put kind of sumps like you might find in basements throughout the upper Midwest, and we collect the drainage water from individual tile lines and monitor that for water quality and how much water flow, so quantity of flow, is coming out of each of the plots where we've implemented some type of treatment. And just a nice every presentation needs a nice aerial photo, right? So we got a nice aerial photo of one of our sites in Northwest Iowa, where if you look at kind of about to the middle third, you'll see kind of that's where the sumps are, and the plots drain into those sumps. You'll see some light colored corn out there. That may make more sense here in a minute, because that's one of our treatments that is low in nitrogen, and so the color of that corn is not what we would like to see. Okay, and this is just what it looks like in the field. Just wanted to illustrate this is not trivial to do this type of quantification of the nitrate loss from our nitrate loss through drainage from our cropping systems. Okay, so the nutrient management, and we'll talk a little bit about some of these. So kind of in broad categories, some of the things that we're thinking about are really looking at our nitrogen application rate. And so if you want more information, there's a corn nitrogen rate calculator online, and there would be for different states an estimated maximum return to nitrogen rate that would be applied. And so that would be one of our first practices to think about implementing is making sure we're applying the appropriate nitrogen application rate. And I'll show you kind of how the nitrogen application rate impacts nitrate loss that we see coming from our system. We can think about product, things like nitrification inhibitors that may slow that conversion of ammonium into the nitrate form. So if we apply anhydrous with an inhibitor, we want to delay the conversion of that anhydrous ammonia into the nitrate form. And some of our nitrification inhibitors may help us do that and help us have a potential for reducing nitrate loss. We can also look at split application of N fertilizer. So maybe we put on some before planting and then some in season, like you see our low-tech picture of late season nitrogen application for our system. This is up in Northwest Iowa, where we have a Gandy drop spreader where we're applying nitrogen on into that very large standing corn crop. And we'll talk a little bit about what that does, what we've found, the potential for that for reducing nitrate leaching. And then in many areas of the Corn Belt, thinking about moving to a spring N application. This is one that I think the impact of it is going to vary depending on where we're at. In many areas that we're at in Iowa and Minnesota, where most of our drainage comes in the spring of the year, so not during the winter months, we probably see little impact of reducing nitrate loss by moving from a fall anhydrous application to a spring. But as we look at maybe a little more east in the Corn Belt with a lot of winter drainage, moving from if we are applying in the fall to the spring may have greater benefit. So other infield management practices that I think are important to talk about as we think about nitrate loss, at least because we hear a lot about it, and the results may not be exactly what we would might expect or maybe want, but things of reduced tillage or no-till, so maintaining soil cover out there. There would be a lot of benefits of having a system that looks like the one you see in the picture from a soil protection standpoint and maybe a phosphorus runoff standpoint, but we'll just be prepared. We'll talk a little bit about how no-till might, what it might do from a nitrate loss perspective. And then probably one of our bigger ones as we think about in-field practices, specifically while maintaining corn soybean production, is cereal or cover crops, excuse me. And in a lot of our areas, we may be using winter cereal rye. So here's a couple pictures from quite a good growth of winter cereal rye here in Iowa, and we'll show you some of the benefits that we get from that from a nitrate reduction standpoint. Again, if we have this growing out there, if you think back to that red line and green line, by having this crop out there during kind of that late March, April, maybe even in early May, that the red line from our nitrate production might still be happening, but now we have the green line taking up some of that nitrate that's been converted from organic nitrogen into the nitrate pool. So kind of putting that into above ground and below ground biomass, reducing the risk of nitrate loss for excess precipitation that may move through the plant root zone. Okay, and if we look at, there's been a number of studies done and some work done to try to compile information about the performance of many of these practices that I just talked about. And some of this was summarized in Iowa nutrient reduction strategy, Illinois nutrient loss reduction strategy, and the Minnesota nutrient reduction strategy. And you can see here, this is kind of some of the performance of practices. And what I've circled, or not circled, rectangle, the purple rectangle there is most of our in-field practices where we still have a annual row crop production. You'll see some of the green ones up at the top of pasture and hay, perennial energy crops, maybe even extended rotation. Those are broader land use conversions that we're maybe moving away from as much corn and soybean production. But the mustardy or yellow, dark yellow colors in the purple rectangle down there below are many of those infield practices. So you can see here, for example, nitrification inhibitor. If we're using that nitrification inhibitor, we might expect about on average, maybe a 8 to 9% reduction in nitrate loss with a nitrification inhibitor based on the data that we summarized for the Iowa nutrient reduction strategy, about 10 in Illinois, and maybe about 13 or 14 in Minnesota. So you can see kind of single digit impacts of that. If we look at something like a cover crop, if we compile all that data from many different data sets, you'll see that nitrate reduction estimated to be for the rye about 30% in Iowa, about the same in Illinois, and about a little less in Minnesota. Okay, that kind of makes sense. Why might it be less in Minnesota, you might ask? Okay, well, I think one reason is it's a little colder in Minnesota. It doesn't warm up as early in the spring to get some of the spring growth of that cereal rye, or it may get colder earlier in the fall, so we don't get as much fall growth. So as we think about a cover crop, one of the things that I think is very important is how much growth above ground, below ground, and mainly we monitor above ground biomass. If anybody's interested in doing lots of root ingrowth of crops, have at it. It's very important, but many of us don't do it because it's a real challenge. But the take-home point is, if we get more biomass of that cover crop, we would expect to see greater reduction in what leaves the plant root zone from a nitrate perspective. Okay, I guess one of the other things that I don't have slides on too much, but if we apply from some of our research in Iowa, if we apply similar nitrogen application between commercial fertilizer and liquid swine manure, for example, or poultry manure, if we apply similar nitrogen rates at similar time with similar type cropping systems, we see very similar nitrate loss between those. And so you'll see, actually in the data that we summarized, it was about a 4% reduction in nitrate loss with the liquid swine manure compared to commercial fertilizer, and poultry manure was about a 2 or 3% increase in nitrate loss with the poultry manure. But as you can see with those points, as well as many of the others, that for the Iowa information, that black line is the error bar, standard deviation, plus or minus 1 standard deviation. So you can see these are very kind of dynamic systems. One year you may see benefit, the next year you may not see a benefit, or actually, an increase, because very dependent upon the precipitation patterns. Okay, so we're going to talk a little bit about some of what we see from infield management. I'm going to talk about mainly data from 3 different sites in Iowa, and we'll first start at our Gilmore City site. So I bring up this slide to illustrate kind of how nitrate loss from our corn soybean cropping systems varies from year to year, and that it's very dependent upon how much precipitation we get and how much drainage that we get from our systems. So this is following 30 years of a corn soybean cropping system with essentially the same agronomic management of the crop, essentially the same type of tillage, the same timing of nitrogen application for that corn crop, and the same nitrogen rate for that corn crop, 150 to 160 pounds of N per acre. And what you'll see is that let's start with the green squares. That's the annual drainage. And so in 1993, it was very wet in north central Iowa. We had 27 inches of drainage, the equivalent of 27 inches of drainage. So over 50 inches of rainfall, 27 of that left the plant root zone and was captured with our drainage water. Okay. So, and the next year we had about an inch of drainage. So very variable year to year. You can see the nitrate loss, which is the triangles, orange, red triangles. That pattern of nitrate loss follows closely with how much drainage we get. Kind of generally in years with high drainage, we see high nitrate loss. In years with low drainage, we see low nitrate loss. In general, couple kind of areas that are a little bit different are in the early 90s period. We had multiple wet years that tended to leach our soil profile out. So the nitrate concentration that started in 1990, so this is the blue circle, is the flow-weighted annual nitrate concentration. It was about 17 in 1990. When we had multiple wet years, we leached that out. It was down to about 7, okay, in that year. I think following through and thinking about what we see with that blue line is very important. If we had just monitored those first 4 years, we would have said we're having a positive impact from our management on reducing nitrate loss, because it went from 17 down to about 7 from a flow-weighted annual nitrate concentration. But really that was due to the weather that we had in those years. And so then we see multiple drier years, and that nitrate concentration that we had annually was, wet up over 20 in 1999. And a really good example is here. Hopefully you can see my mouse pointer. In 2012, we had a drought. We had nitrate concentration about 15 in the little drainage that we have. In 2013, it jumps from 15 to 21, the highest over the 30-year period. So that drainage post-drought, we had stored a lot of nitrate within our soil profile. We got drainage. We got excess precipitation and movement of water through the soil profile. It took a lot of nitrate with it, and we had high nitrate concentrations in that year. That was, using the same management, we still got a jump of about 7 parts per million for a flow-weighted annual nitrate perspective. Okay, so as we think about the 4 R's of nitrogen management, I think it starts with the nitrogen application rate. And so this is a curve that relates the flow-weighted annual nitrate concentration to the nitrogen application rate in a corn-soybean rotation, where that nitrogen is primarily applied to the corn crop. There was a system in here, some of the newer data with these orange triangles to the right, there was manure to both corn and soybeans. But in general, the black dots are data from Gilmore City that were used to generate this purple curve. So kind of the take-home point here is that couple take-home points, okay? One is, even when we apply no nitrogen to a corn-soybean cropping system, so this is nitrogen application rate of 0, we still see nitrate concentrations between 5 and 12 parts per million in our leachate, in our drainage water, okay? Drinking water standard of 10. So we still see some nitrate loss, even when we apply no nitrogen in a corn-soybean cropping system. Think back to that red line, green line issue, because we still, we have that red line and we have the green line. We have susceptibility to loss, even when we apply no nitrogen. The second is that this curve of increasing nitrate concentration with increasing nitrogen application rate is fairly, the slope is fairly flat until we get to maybe 120, 130 pounds of nitrogen per acre. And then it kind of a little bit of an exponential increase as we move beyond that. So, if we adjust nitrogen rates, 100 to 120 pounds, maybe not as big a difference. But if we're up over here 200, 215, and we adjust, it may have a bigger impact on reducing the nitrate concentration. So let's think about that. If we had, here we go. Here's say we started with a nitrogen application rate to corn in a corn-soybean rotation at 180 pounds per acre. Okay, we would estimate the flow weighted annual nitrate concentration of about 16.5 milligrams per liter or parts per million. And then say we wanted to move that application rate down 30 pounds. So we're going to go from 180 to corn and a corn soybean rotation down to 150. You can see here's my 150. I'm going to go over, and that's going to be 13.3 actually. I know that one. I know the curve. I can remember what it is at 150. Okay. So we went from 16.5 to 13.3. Okay. So let's look at what percent reduction that is. So 16.5 minus 13.3. So that's a 3.2 milligram per liter reduction out of that 16.5. We have about a 19% reduction in nitrate concentration by reducing that nitrogen application rate, in this case from 180 to 150. Okay, so that could help us reduce nitrate loss. If we look at many of these, the goals that we have in upper Midwestern states is for a 45% reduction statewide in nitrate exported downstream. I think that, kind of looking at this illustrates we're not going to get that 45% reduction just by reducing nitrogen application rate. We're going to need some of the other practices that we'll talk about because our maximum return to nitrogen rate is probably somewhere around 150 in Iowa. So if we went from 180 down to kind of the recommended rate based on the corn nitrogen rate calculator, it'd be about 150 in there. Okay, let's talk a little bit about some of these other infield practices and their potential impact on nitrate loss. One of the other ones I mentioned was tillage. So there are many reasons why no-till may be important. As we look at some of the meta-analysis that's been done looking at the impact of no-till on nitrate loss, really what it's found is very little impact. And we have some data in Iowa that kind of illustrate similarly. So, but what we might find is that it can vary in time, the impact. So this is following a no-till system implemented in 2010 and following it for the next 10 years. Okay, so the first, the no-till, as I said, implemented in 2010. The circles and red line is the cumulative nitrate loss from the conventional till corn soybean system. The squares, yellowish, is the cumulative nitrate loss from our no-till system. And what we find is in the first 5 years, we reduced nitrate loss about 72 pounds with no-till, but in the second 5 years, very little impact, about 13 pounds out of, so definitely less than a 10% reduction in that next 5-year period. So illustrates that some of these practices that may change the soil biology may differ in how they perform over time. And so this is, I think, kind of interesting to see that, this tillage practice, we may see a difference in how well that performs from a nitrate reduction standpoint, depending on how long we've implemented it. I think there's kind of a need. This kind of illustrates the importance of monitoring and documenting nitrate loss for a long period of time, because just monitoring for 3 years or 5 years may give us one conclusion, but because these are soil systems, dynamic, different weather conditions, different changes in soil health and soil quality, the performance or impact may change over time. Okay, now let's look at cover crops. So this is a similar site at our Gilmore City site. This is a system where actually we have some tillage with and without cover crops. So CT is our convention or conservation tillage. CTR is conservation tillage with a rye cover crop. And if we look at this over a 10-year period, we reduced nitrate loss, nitrate delivered out of that drain with a winter cereal rye cover crop by approximately 111 pounds per acre. And so pretty substantial reduction so that's about 11 pound per acre per year nitrate reduction with the use of that winter cereal rye cover crop. I'd also say this is in north central Iowa, where we don't consistently get the best growth of cover crops year in and year out. So we still got a pretty substantial benefit of the cover crop in reducing nitrate delivery, even in an area that we probably didn't optimize cover crop growth. One of the things is that, again, kind of to illustrate that the importance of looking at these systems for as long a time period as we can. So here's looking at our no-till, which is the yellow circles, or excuse me, the yellow squares there is our no-till system. The green triangle is the no-till with winter cereal rye. Both of these systems were implemented in 2010. If we monitor that first 5-year period, we saw no difference in nitrate loss, no reduction essentially with the winter cereal rye cover crop. Okay, if we just stop there, we would say, oh my gosh, cover crops don't help us. But then we monitor that next 5-year period, and we saw a 46 pound per acre cumulative reduction with the winter cereal rye cover crop. So, again, kind of highlights the importance of long-term monitoring of these systems to work to document how well they perform in reducing nitrate loss from our corn soybean cropping system. Okay, we're going to move on to Northwest Iowa, and we have, this is to highlight a couple of two of our 4 R's again, rate and also the timing of nitrogen application, okay? And so what we have is, I'm going to just show the results here and walk through the treatments that we have. We have a no nitrogen treatment where the plots stay the same every year. They just rotate between corn and beans. And so we've gone 7-8 years without any nitrogen application to these plots. We have a system with fall anhydrous with a nitrification inhibitor, where that fall nitrogen is put down when soils are 50 degrees and cooling, or at least when the soil temperature is below 50, okay, and trending down. We have a spring pre-plant anhydrous, and we have a split nitrogen application with urea at planting and Agritane treated urea in season. If you remember back the picture I showed you of the Gandy drop spreader into standing corn, that's our split end treatment. Okay. What we found is that this is broken down by the corn phase and then the soybean phase. What we found is that no significant difference in flow-weighted annual nitrate concentration between fall nitrogen or spring nitrogen. We see a reduction with the split N or the no N. Okay, so I'm gonna jump here to one other factor here before I move on is if you look at the nitrate concentration between the corn year and the soybean year, and again, we're only applying nitrogen in the corn phase, but we see similar, in many of our sites, we see a similar nitrate loss in the soybean year as we do the corn year. So you can see here, our nitrate concentration is about 11 in the soybean phase for both the fall and the spring, and it's about 11 to 12 in the corn phase. So very similar nitrate concentration and ultimately losses between the corn year and the soybean year at many of our drainage sites. Okay. As we combine then our corn soybean cropping system for 2015 to 2020, what we see is, again, no difference essentially between fall N and spring N. We see about a 10 to 15% reduction when we use the split nitrogen application. So this is that timing. Okay, so there are multiple timings. So one would be fall to spring. We didn't see an impact. But if we look at fall and spring compared to this split application, we do see the split application helps us reduce nitrate loss. Again, though, there are kind of limits to what we can expect there. And even when we apply no nitrogen, we still see about 8 parts per million as the nitrate concentration leaving that plant root zone. So, as we think about a 45% reduction, at this site, even when we applied no nitrogen, we're probably only at a 30 or 40% reduction. And we need to get that 45, which really kind of illustrates our infield practices. We really do need to consider things like the cover crops that we talked about before. One slide to highlight the agronomic impact of these practices, okay? And this is the biggest takeaway. There's a lot of data here, though. Biggest takeaway is when we apply nitrogen, we increase corn yield. Okay, I'm not telling you anything anybody doesn't know, right? I mean, if we found something different, then that people would say, well, we shouldn't be applying nitrogen. But okay, so the biggest thing we see again, when we apply no nitrogen, we get lower corn yields than when we have the fall, the spring, or the split application. The next thing is in 5 of the 6 years, we saw no statistically significant difference between a fall, a spring, or a split nitrogen application. Or on average, if we look at the average, it's almost the same between fall, spring, or split. However, in 2017, we saw about a 20 to 30 bushel yield decline with our split nitrogen application. And you might ask why. I think that because it was the same total application rate of nitrogen, 135 pounds of N per acre. But if you think back to that Gandy drop spreader in one of the earlier slides, that was put on when the corn was pretty big. And we only got 1 inch of rain in the month post putting that Agritane treated urea on the surface. And so I don't think that nitrogen got down to the plant root zone to be effectively used. So I think it's just something to kind of think about, that we need to make sure and understand there could be some risks with some of these practices based on the weather conditions that we might have. In this case, we put down 45 pounds pre-plant and then came back with 90 later in the season. Maybe we want to put a little bit more down pre-plant and require a little less on the in-season application to mitigate risk of any decreased corn yields. But I would highlight that this is in one of the drier areas of the state of Iowa. It's, northwest Iowa. We're getting toward the western, a little bit more toward the western edge of the Corn Belt, where we might see a little bit more water limitations during the growing season. Okay, going to highlight one other kind of thinking about timing and timing with cover crops at our Northeast Research Farm site. And this is, we're looking at manure. And so what we're looking at here is cases where we are applying liquid swine manure really early in the fall, right after soybean harvest, okay, versus later in the fall when soils are 50 degrees and cooling. I often ask, some producers, would you apply commercial nitrogen, in our case, maybe anhydrous, at the same time that you see some of the liquid swine manure going down? And it's pretty much universally no, we would not apply it. But there are logistical reasons why individuals may apply that manure early in the fall, because they're worried about running out of pit space and so forth. But so, okay, if we apply the manure early in the fall, you can see over that 2016 to 2019 period, our nitrate concentration, the annual nitrate concentration was about 20 versus about 12 to 13 if we did early manure with a winter cereal rye cover crop or the later manure. So this was a study to look at, if we increase nitrate concentration and loss with early manure application, can we mitigate that risk with a winter cereal rye cover crop? And we were effectively able to do that. If you look at this top pane, we reduced that concentration from 20 down to about 12 or 13. And then if we applied it later in the fall, it went from 12 to about 14. So in both cases, if we applied it later or did the manure with cover crop, we could reduce that nitrate concentration and loss. You can see in the subsequent soybean phase, we really saw no difference if the manure had been applied early or late to the prior corn crop, but we did see a benefit when we were growing a cover crop. So reduction where we had reduction in the soybean year. We were using cover crop both before corn and before soybean. So reduction in nitrate concentration where we had used early manure with cover crop system in the soybean year. Again, and as we think about that manure application and early manure application, one of our big findings from this was the impact of delaying that manure application a bit later in the fall has on crop production, which we really can think about it for profitability for the farmer. So this is looking at 2016, 2017, and 2018, that corn yield. And so we can look at this system 2, which is our early fall manure, versus system 6, which is our late fall manure. And in 2016, we saw 194 bushels with late fall manure, 168 with early, so a 26 bushel yield benefit from delaying that manure application. In 2017, we saw a 63 bushel per acre corn yield benefit from delaying that manure application. And in 2018, 29 bushel. So pretty substantial yield benefit. Importantly, what we saw was that in the corn yield, where we had the early fall manure and cover crop, was the same or better in 2 of the 3 years. Actually, statistically better in 2018, a 16 bushel yield benefit from the system with early manure plus cover crop. But in that first year when we used cover crops, we did see a yield hit. And so just something to think about with that cover crop. But really kind of illustrates if we can delay that manure application, we can reduce nitrate loss, and we can improve our corn yield. We get better nitrogen utilization of that system, of that nitrogen that we've applied. Okay, our last site that we're going to talk about in our last system is really looking at broad scale conversion of our land use. And in this case, what we're looking at is a prairie. So in 2008, we went into a system, we put new drains in, and on 8 of those individual drain plots, we planted a diverse mix of prairie. Okay, 4 of those plots received nitrogen fertilizer, about 75 pounds of acre per year since that point in time, and 4 of those did not. And so what I'm comparing here is a continuous corn system. That's the top curve. The next one is continuous corn with a winter cereal rye cover crop. And you'll see that we reduced nitrate loss from about 145 to 111 or 112 over that at that 10-year period there with use of the winter cereal rye cover crop. So we got some benefit. But when we had something growing out there all year, like our prairie, cumulative nitrate loss was below 10 pounds per acre over a 10-year period. Cumulative loss, not annual loss. Cumulative loss was less than 10. And we saw very similar nitrate loss between the prairie and the fertilized prairie system. In fact, because of plot-to-plot variability, actually a little bit less from the fertilized prairie. But in general, if we have something growing out there year-round, we have great potential for reducing nitrate that's lost below the plant root zone. So we really have to think about how can we have living cover, living roots on the land a greater percentage of the year, and we can have a positive benefit on reducing nitrate loss. Okay, so now let's kind of summarize what we've talked about and maybe return back to maybe an initial question as we think about this module, which is, can infield conservation practices help us reduce nitrate loss? And I would say in a general sense, absolutely yes. But their performance, their ability to do that is going to vary, and it may be very year to year dependent. So one of the things that we often think about is no-till from an infield conservation practice standpoint. I think from a nitrate loss perspective, that would probably be a practice that we might say has limited impact, or that impact might vary over time. If we think about timing of nitrogen, I think we can see an impact, but again, that impact is going to vary depending on where we are in the Corn Belt and the type of year that we have. If we have a year with a lot of winter drainage or early spring drainage, we might expect that to see more nitrate loss from a fall nitrogen application than if we had a spring nitrogen application, but it may be very year dependent. Because from our data in Northwest Iowa, we didn't see any difference over that time period, but that is a location without a lot of winter drainage on a consistent basis. I really think, though, as we think about infield practices that can reduce nitrate loss and reduce that leaching below the plant root zone, cover crops hold a great potential while maintaining corn soybean production, but we need to get growth of that cover crop. And then a perennial, and in this case, I'm highlighting prairie, can dramatically reduce N loss. As we showed, if we have something growing out there year in and year out, a great percentage of the year, we can dramatically reduce the nitrate that's lost from our cropping system. So with that, this is my contact information, and I hope that with this you learned a little bit about the performance of various infield conservation practices in helping us reduce nitrate loss that's lost from the plant root zone, and then when we're thinking about in the drained landscape, lost through our drainage system. So with that, thank you very much for your attention.